All right. Hello to you all. What I'm going to be doing with you right now is giving an example um, of vector addition, where we're adding two vectors together to find what's known as the resultant. The result of adding those two vectors together produces a new vector called the resultant. And in this case, I'd like to do it a little more quantitatively, since in previous Zoom meets that were over the summer, I did describe the concepts behind vector addition. It was more conceptual. So this is an opportunity for me to show a vector addition problem from A to Z in terms of all the mathematical steps you would need to know how to complete in order to perform vector addition. So let's begin. I'm going to try black. Let's try black. And bear with me, the smartboard usage is somewhat new to me. Not somewhat, it's very new to me. I'll do the best I can, I'm sure. I'll get more used to it as I continue using it. All right, so let's draw two vectors. I'm going to draw vector A. I'm going to call this vector A. And this little symbol I wrote here over the A is the vector symbol. So it indicates that this quantity that I'm referring to as A is actually a vector, and its name is vector A. And then we're going to look at vector B. Now, vector A and vector B can technically be any length. That means they can have any magnitude. The word magnitude indicates references how long the vector is, the magnitude, which represents the quantity, some quantity that you're trying to represent. So if this was a velocity vector, if vector B was a velocity vector, and the physical length of that vector was 30, then in an application problem, the velocity of the wind might in fact be 30 meters per second. And if the wind increased in its speed, then the magnitude or length of the vector would get longer to indicate that the speed of the wind has increased. Or if it got shorter, you'd say the magnitude is decreased for this vector to indicate that the speed of the wind has decreased. Okay, so these are two vectors. Again, they can be in any particular direction. They can be any particular length. Just like adding two numbers, they can be any numbers you want. When you add them, you get some third unique new thing. 4 plus 2 is two unique things, but when you add them, you get 6, a new unique number that's not the same as 4 or 2. Similarly, we're going to be adding these two vectors together to produce a third vector, which is not the same as either of these two. And that third vector is referred to in math and in physics as the resultant vector. So let's first just visualize it. The visualization part is fairly important. In fact, let me see if I can show you a good visual here. Give me a moment. So I should be able to stop sharing the whiteboard. Then I can hit present now again. Give me a moment. And now I'd like to share this tool. So you should be seeing this now. So there's vector A and vector B. Maybe not exactly the way I had drawn them before, but I'm pretty close. So if we were to add these vectors together, we would place them head to tail. It's called the head to tail method for vector addition. The head of a vector is the arrow, the end of the arrow, the pointy part. That's called the head. And then the back end of the vector is called the tail. So when you're doing vector addition using the head to tail method for vector addition, you place the tail, the back end of this vector B, against the head, the tippy top point of vector A. That's called the head. You stick the head and the tail together. So once they're connected, you've now added those vectors visually. If you wanted to see the resultant vector in terms of what it would look like, you would always draw the resultant vector from the beginning the tail end of vector A all the way to the end, the head of vector B. So what does that mean? What does that look like? Right here. Now they've called it vector S, which is fine. You can call it anything you want, but technically it's called the resultant vector. The resultant vector, again, is a third vector. It's not the same as vector A or vector B. And its magnitude is the straight line distance between the beginning, the back end of vector A, to the end, the head of vector B. It's referred to as the resultant. Notice its length is different than the length of A or the length of B, and therefore its magnitude will be different, the numerical value for its length. And its direction is not the same as the direction of A or the direction of vector B. Our goal in adding vectors together is always to define the new vector, the resultant vector, in terms of its length, magnitude, and its direction. And that's what I'm going to show you now. So let me switch back. Give me a moment. Switch back here to present just a window back to here. All right. So before we actually add these the way I had shown there, first what you want to do is resolve vectors into their components. So a two-dimensional vector technically has two components. One component that's along one dimension, like the x-axis. When we think about the x and y-axis, here's our y and x axes. Any vector that's a two-dimensional vector, for example, like this, like I could call this vector A here that I just drew. If I can see the length of the components that are parallel to each of those axes, then those parallel pieces parallel to each axis is called the component of that vector. So in this example, I don't know why it's green. It's supposed to have been red. So this piece right here, which is not working, I'm not sure why. This piece right here, that would be considered the x component of vector A, and usually you would write it, I'm not sure what's going on with the marker right now, AX. That's supposed to be a little x to indicate that that component that I just drew in is the x component of vector A. It's parallel to the x-axis. And then this one here is the y component of vector A, because it's parallel to the y component. So whenever you're drawing a vector, and this is technically a first quadrant vector that I've drawn, it's technically, you can have a vector that's in quadrant 1. A quadrant 1 vector, the direction of the vector is between 0 and 90 degrees. But for quadrant 2, which could be, let's say this way, remember that this is 0 degrees, this direction here. Straight to the right is 0 degrees. Straight up is 90 degrees. Straight to the left is 180 degrees. Straight down is 270 degrees. And then back around is 360. So when you're looking at the quadrant 2 example, the direction of that vector would have to be between 90 degrees and 180 degrees. As long as that's true, then that'd be considered a quadrant 2 vector. You could have a quadrant 3 vector. And I wanted to point this out because technically in the example I'm going to do of vector addition, both A and B, vector A and vector B, are both quadrant 1 vectors. And it's just nice to do that because it's easy to draw and it's a nice starting point. But I wanted you to recognize that that doesn't always have to be the case. So in quadrant 3, if you've got a quadrant 3 vector, maybe it's something like this, then the direction of that vector has to be between 180 degrees and 270 degrees. Makes sense? Right. And then lastly, quadrant 4. The quadrant 4 vector would have to be between 270 degrees. The angle theta has to be between 270 and 360. Now and this would be maybe one like this. Now I want to point out that if you are drawing components, that can sometimes be confusing for students. So let's just say I wanted to draw the components of my quadrant 1 vector. Start at the tail. Again, this is called the head of a vector. And then the back end is called the tail of the vector. So if you're trying to draw in the components of a vector, start at the tail. And your goal essentially is to draw two lines that lead you from the tail to the head, but you can only move either perfectly horizontally or perfectly vertically. So if my goal is to start here, then I'd have to move to the right and stop right there. And then I'd have to go straight up to get to the ending point there. And I say that because sometimes students are looking at quadrant 1 vectors that look like this and drawing the vertical component up, which is correct, but the horizontal component is backwards. They're drawing it to the left. So always, again, think of starting at the very bottom of the vector, the tail, and you're drawing two perpendicular lines, one along the x-axis and one along the y-axis, to get to the head. So in this case, for quadrant 1, you have a rightward and an upward, a rightward component for the x component and an upward component for the y component. If I was drawing my quadrant 2, follow the same rule. Start at the back end. This component would go all the way to here. And then I would have a little bit of a y component right there. For quadrant 3, I'd start at I didn't draw quadrant 3 very nicely. Very neatly, I should say. Try again. So if this was quadrant 3 going down like this, then the x component goes to here and the y component goes down. Or for quadrant 4, I see an x component that goes from here to here and then a y component that goes down. Okay, so that's just giving you a just description again of how you visualize quadrant 1, 2, 3, or 4 vectors, and then also drawing the components is an important part of vector addition. To visualize it, in my opinion, is quite important. So I'm going to now erase all that. And this takes a long time, so I haven't even discovered is there, other than wiping my whole screen off, which would probably still be quicker. That's what I'll do. Just clean the whole thing off and just start over. So, all right, let's begin. So we got vector A, which looks like this. And I would now draw in the components, the x component of vector A and the y component. And that has a certain direction associated with it. From what I can tell, it looks like it's about 45 degrees in this example. So I'm going to jot that down. So now we're also going to look at vector B. Vector B is less than 45 degrees, but greater than 0 degrees. And so I'm going to draw in those components. Here's the x component bx and the y component by. And perhaps this angle is, I don't know, say it's 20 degrees. So that means I now have two vectors, but I will need the directions of both vectors and the lengths of both vectors, the magnitudes of both vectors. I haven't given that information yet, so I would draw that as the magnitude of vector A is, can be any number. I'm going to pick the number 30. And the units could be whatever the vector is representing. If these are speed, or I should say, if these are velocity vectors, then those units could be meters per second. If this is force vectors, then those units would be newtons. If these are acceleration vectors, those vectors would be units of meters per second squared. So the unit depends on what quantity it's representing, what vector quantity it's representing. But in this case, I'm just going to say units. Just arbitrary units, I don't know. Could be displacement vectors, in which case those are just meters. All right, and let's give a length to vector B, magnitude to vector B. We'll say is, well, it looks maybe a little shorter than 30, a little shorter than vector A. Let's just say it's 25 units long. And again, just so that's clear, the length, oops, not sure what happened there. The length of the vector is the length along the hypotenuse, right? That's considered the vector. And so it's 30 units long. Or in this case, this one was, oops, this one was 25 units long. So visually, that's the length of the hypotenuse. Right? Okay, so let's just say we now want to add these vectors together. If that's the case, you first have to determine how long is the x component for vector A and how long is the x component for vector B. And similarly, you'll have to answer that question for the y component, which I didn't draw in here yet, the y component of vector A as well as the y component of vector B. You have to physically do some trigonometry. So let's just start with getting AX. I'd like to figure out how long this one is, assuming that the length of the hypotenuse is 30 units long and the angle is 45 degrees. So in this case, I've got an adjacent, because this is adjacent to the angle of 30 degrees, and I also have the hypotenuse. So I know the length of the hypotenuse, and I'm looking for the adjacent. So I'd have to think which trigonometry function goes with adjacent and hypotenuse. Right, so that would be our cosine. Our cosine of some angle is considered the ratio of the adjacent length divided by the hypotenuse length. So our adjacent length is our unknown AX. So I'll just take away adjacent and put AX. The hypotenuse length is technically 30, right? I'm doing some math now to solve for the length of AX. I can put this over 1 and I can cross multiply. AX times 1 is just AX. And then 30 cos of the angle, theta, which I didn't draw in. What was the angle? It was a 45 degree. So I'm going to put a 45 degrees here. So I know that the length of this one right here, AX, is 30 cos 45. So this length is 30 times the cosine of 45. Now, cosine of 45, well, that can bring you back to your one of your special triangles where you have a 45, 45, 90, right? And the legs, excuse me, the legs are both the same length, but because of Pythagorean theorem, where c squared, which is usually the hypotenuse, c, is equal to one leg squared plus the other leg squared, right? Which is 1 squared, which is 1, plus 1 squared, which is 1. Well, that's 2. And so you'd end up with c squared equals 2. And then if you solve for c, you'd get root 2, right? That's why you get this 1, 1, root 2 relationship. And so what is cos 45? Cos, again, it's written on the board, adjacent over hypotenuse. So you could pick either one of these angles up here. I'm going to pick this one. Adjacent would be the number 1, and hypotenuse is root 2. So cos of 45 as a ratio is really the number 1 over root 2. That happens to be 0.707 because that's a common one that I have known from just the years of doing this stuff. 1 over root 2 is 0.707. So it's a decimal. It's a ratio of a short length for this segment here, which is divided then by a longer length, which is the hypotenuse length. So it has to be a number less than 1, right? So technically, to get this answer, I'd be doing 30 times 0.707. And that would be an estimate. If you wanted to keep the answer exact, you would just type into your calculator and make sure you're in the right mode. You have to go to mode first and make sure that the unit for degrees is in, that the unit for the angle is in degree mode, not radian mode. So I'm going to type in 30 cos 45 if I want an exact answer. I get 21.21. units. However, it is an estimate or approximation. Of course, if I had done 30 times 0.707, I would get the same number, 21.21, right? Okay, so that's the x component. I don't even have to necessarily do the y component because I'm being aware enough of the fact that this triangle, since this vector A was a 45-degree vector, that the legs of the x leg, the x component, I should say, and the y component leg are the same length, right? It's to say that the length of this one here is exactly equal to the length of this one. And I already just determined that the x component was 21.21. Well, then the y component must also be 21.21. Had I done that, out mathematically, you would have used a different trig function. So if that were the case, you'd be saying, well, I'm looking for the opposite length if this was in fact unknown. This is opposite to the angle. And I know the hypotenuse, so I would have used sine. I'd say the sine of 45 degrees equals opposite over hypotenuse. And I'd say, well, the opposite is AY over the length of the vector, the magnitude, which was 30. And you would do the same sort of thing. You cross multiply, you end up with AY equals 30 times the sine of 45. But we already know that, again, the sine of 45 and the cosine of 45 these are equal because of the 1, 1 root 2 triangle, right? So when you're looking at that triangle, if you did pick one of the 45-degree angles, let's say this one, and did what is cosine of 45, it would have been 1, because this one right here is adjacent, over root 2. What if we use that same angle and we say, what's the sine of this angle? Well, that's the opposite, which is 1 again, over root 2, right? So sine of 45 and cosine of 45 is, in both cases, equal numbers, which is 1 over root 2. All right, so now I'm going to move on to vector B. I'm going to clean this board up a little bit if possible. Okay. It must be a larger eraser. I'm sure there has to be. Just don't know where to access that. So apologies if this is taking a little while. All right, so now we look over at vector B to do the same thing. We need to figure out the x and y components for vector B. Remembering this one was 21.21. I erased that by mistake. And so was AX. Right, they were both 21.21. I'll just AX also equals 21.21. All right, so I'm going to make this a little quicker for you now, right? Just remember that the x component of any vector is always the length of the physical vector, the magnitude of the vector, times the cosine of whatever direction or whatever angle that vector forms with the horizontal, called the direction of the vector. So this is always true. And the y component of any vector is always the length or magnitude of the vector times the sine of that vector. I'm sorry, times the sine of the direction of that vector. Oops. I'm not sure why I did that. And the reason being because, like we said, if this was the cosine and you said cosine of this angle over here, cosine of 20 degrees is bx over 25, the hypotenuse is 25. Well, I could just put magnitude of b there. And if I just don't put numbers in and just say, what is the general formula for this? Bx times 1 is bx. And then b times cos theta gives me b cos theta, right? So in general, I know the x component is always matched up with the cosine function, but you have to multiply it by the length of the vector, the magnitude. And if we similarly did the same thing for the sine, definition of sine, which was opposite over hypotenuse. Well, opposite is technically by over the hypotenuse, which is the length of the vector. And at the same sort of cross multiplication, you get by times 1 is by, magnitude of b sine theta, right? This is in your textbook. This is shown in your textbook that this is just a general format that you use for finding components. So you're not having to, once you know this, you just take out the tool and you use it. You don't have to work through all these steps all year long whenever you're dealing with something that's vector related, right? So moving forward, that's what I'm going to be doing. I'm going to just be using this formula. You see now where it comes from so that I can save some time. So for vector b, some numerical values here. For vector b, the physical length of vector b is was 25. So I don't really need the absolute value symbols there anymore. I can just get rid of those as well. So 25 is the length of the hypotenuse for vector b, and the angle, the direction was 20 degrees. Now that doesn't bring us back to any special triangle that you might learn in a geometry class, so I'm going to have to type that stuff in. 25 cos 20. I'm going to round that off to 2 decimals. I get approximately 23.49 units. And now when I do for the y component, type 25 sine 20, which is 25 multiplied by the sine of 20, I get approximately 8.55 units long. So now I know how long all 4 components are, and I'm ready to do some addition. Here's why. I'm going to bring you back to that visualization tool. So let's go back to that now. Window, let's see, just here and share. Okay, so if I were to go here and remove this here, if I wanted to see again the components, here they are. Here's the visualization of those components. This one right here is AX, this is AY, this is the length of BX, this is the length of BY. And to be honest, I don't know that I think it's pretty similar to what I drew. I'll stick with it. So those are the components, right? We need to know how long this piece is and this piece is because we're ultimately trying to find the resultant, which is this vector, right? And so just looking at this, if this is what we're ultimately after the length of the hypotenuse of this purple triangle, called the magnitude of the resultant. But to know how long this piece is, we need to know how long this piece is, the x component of the resultant. Well, the x component of this vector is as long as this length plus this length, right? You add the length of ax to the length of bx, you get this length here. I might call it the length cx if we decided to call this purple vector vector c, then this would be called cx. And we also, again, the goal is to find the length of the hypotenuse, but to do that, we need to know how long this one is, which I just described, and we need to know how long this one is. Well, the length of this one here is equally as long as this length plus this length, right? These, when stuck together, this little one here and this one here, make a new y component that's this long, right? And now if you have the length of this and you have the length of this, then you could just use the Pythagorean theorem to determine the length of this piece, the length of the resultant, the magnitude of the resultant, right? Okay, so I'm now going to stop sharing. I'm going to go back to I'm not sure why that's doing that. Did I lose? What did I lose? Did I lose something here? There it is. Share. Okay. So now that we have all of this, these numbers and the concepts behind the numbers, the concepts behind what these numbers represent, my recommendation, if you were doing a vector addition problem, is to make a little table for yourself. And that's what I'm going to show you now. You make it like this. You say, okay, this is going to be, this row is going to represent vector A, and this row is going to represent vector B. And this piece right here is going to represent the X component, because this column is going to be X component right here. And this column is going to be the Y components that we worked out. So this is AX, and I'll put my Y component length there for vector A, and I'll put my X component of vector B here, and my Y component of vector B here. And I'm adding these. And the resultant that we just visualized, I'm going to call vector C for now. A plus B equals C. So this is ultimately, when I add these up, I'm going to get the CX, and then I add the length of AY and BY, I'm going to get CY. All right? So let's stick those in. We know that for the vector A, they were both 21.21. This was a 45-degree angle for that vector. And therefore, they're equally long, 21.21 for both. Now, also pointing out, these could technically be negatives. If this was a second quadrant vector, then the X component would be negative. Again, if this was a vector pointing in this way, in the quadrant 2 direction, then this component that I'm drawing in right here is actually pointing to the left, and that would have to be represented by a negative value. So if it was technically, 13 units long, you technically would have to put negative 13 into your chart here, because any component that's either facing leftward or downward has to be represented as a negative number. And any component that's upward or rightward has to be represented as a positive number. These are all going to be positive just because in this example, we're adding two quadrant 1 vectors together. And quadrant 1 vectors have positive values for both X and Y components. Okay, so now we're going to go over here and erase these and just again add our information in. So BX I had right here, it was 23.49 units long, and I meant to say BX was 23.49 units long, and BY was 8.55. All right, so now I'm going to add these up. 21.21 plus 23.49. I get 44.7. So this value, 44.7, represents the X component of vector C. The horizontal piece of the purple resultant one that we had seen in that visual tool. And when I add the Y components together, 21.21 plus 8.55, I get 29.76. So this value represents CY. Okay, we're almost there. And this does take a little while, but I do believe it's important for students to understand how all these pieces kind of come together. In an AP physics exam, you would never be asked to actually make this super long calculation, by no means. But there's many concepts related to this lesson that I'm providing right now that they would assess potentially in an AP physics exam. Questions that do relate to vectors that are conceptual, that you actually learn or attain a deeper understanding of those concepts. At least it's my belief that you attain a deeper understanding of those concepts if you actually go through these steps that I'm going through. But after you kind of get the main idea, move on. I can do this forever. Okay, so I've cleared out some space for me. Now let us draw vector C. Remember, what we've done is we've added vector A to vector B, head-to-tail method. We've produced a new vector, what we're calling vector C. And what this implies is that the X component of vector A plus the X component of vector B is how we determine how long the X component of vector C is. And it also implies that the y component of vector A added to the y component of vector B is how we determine how long the y component of vector C is, right? I had gone over that. That's what this indicates. So now that we know Cx and we know Cy, they're in our chart over here, let's draw them in just to visualize them. Which one was longer? Looks like Cx is 44 or so units long, 44.7. That's the longest of the two. So I'm going to draw that in arbitrarily long right now and label that 44.7 units. Now, when I draw in the y component, which is roughly 30, that's roughly 2/3 as long, then I should draw this about 2/3 as long. This one is about 2/3 as long as the other, because 30 is roughly 2/3 of 45. And again, that's just me trying to draw it so that it roughly represents the actual um, resultant vector. Oop, didn't mean to do that, sorry. Because if you just kind of randomly draw things without really thinking about how they are in proportion to each other, then you can still numerically get your answer, but it won't visually look very correct when you compare it to maybe something that comes from those visual tools. A little too long, maybe something like that. Okay. So we know this piece was how long? 29.76 units long. All right. So now we're interested in, and again, this is Cy, and this one is Cx. So now we're interested in how long vector C is, the magnitude of vector C. So we'll be using Pythagorean theorem. To indicate that the magnitude of vector C, the hypotenuse length squared, is equal to the x component of vector C squared plus the y component of vector C squared added together, right? That is Pythagorean theorem. And this also implies that what you're after, which is really the magnitude of vector C, not necessarily the magnitude squared, is equal to the square root of the sum of Cx squared plus Cy squared, right? That's just taking Pythagorean theorem and writing it using symbols that apply to vectors, right? And so that's pretty easy to do. So what is Cx? 44.7 squared plus 29.76 squared. And then I'm going to square root that, raise it to the 1/2 power. So let's work that through. 44.7 squared plus 29.76 squared. All right, I got 53.7, roughly speaking. 53.7 units long. So if someone asks me, what is the magnitude of the resultant, which I happen to have called vector C here, I now know that it's pretty close to 53.7 units long from here to here. The last part is to determine in which direction is that vector, the resultant vector. Which direction is it pointing? And we need to be specific. We can't say that way. We can't just draw an arrow, and say roughly that way. This is mathematical. What we're doing, we need to be accurate and precise with what we're doing. And so just remember that, right, 0 degrees is to the right, 90 degrees is straight up, straight to the left is 180 degrees, and straight down is 270. So we know that we're looking at a first quadrant vector. So the direction of this angle theta in here has to be some number between 0 and 90 degrees, right? But to work that out, I happen to like using the tangent function, I should say, to work out what this direction is. So I use tangent, and your textbooks often do as well, tangent of this angle. Remember, tangent is defined as, in general, opposite over adjacent, right? That's your just general definition from a geometry class. So I'm using that now to say, all right, well, what's opposite? Opposite is really my Cy, and the adjacent piece is really CX, right? That's this piece here, because that's adjacent to the angle. So you can use this formula for determining the direction of a vector as long as you know what the components are. Again, if one of those components was negative, if this was a second quadrant vector that we were looking at, CX would have to be negative. And if you plug that in when you do the inverse tan and put the negative in, it will actually give you an angle that is between 90 degrees and 180 degrees. All right, so the very last step, and we're pretty much done. I know it takes a while, but at least we'll be through it. So the very last step here would be to say, okay, I'm looking for, tangent of that angle. That's what we're interested in finding out. CY is actually 29.76 divided by the CX, which was 44.7. And now I would do the inverse tan of that ratio into a calculator. So I technically type second into my graphing calculator, then tan, which gives us the inverse function. And I type in now 29.76 divided by 44.7. Enter. I get 33.65 degrees, roughly. 36. Oops, sorry, not 36. I get 33.65 degrees. So I know I'm done with my vector addition problem because I can now describe the two properties of the vector. The two properties are are its magnitude, which I now know is 53.7 units long. It's the hypotenuse. And I know the direction it points in, which is 33.65 degrees. So let me give you one last visual. I will jot those things down over here. One moment. 33.65 degrees was the direction, and the magnitude I said was 53.7. Okay. So had I done one last visualization here, stop sharing. To here and here. Again, so the magnitude, which was 53.7 units long, is the length of this purple hypotenuse from here to here. And the direction which was 33.6 degrees or so, is the angle between here and here. That's the direction that this resultant vector points, 33.65 degrees. And had you actually done this to, done a similar problem to just practice it, see if you can pull all these components and pieces together. I'm just going to point out that you can Google vector addition calculator. Seeing if there's any on here that I have used before. Let's try this one. Yep, so here's one. I actually have used this before. So you can add up to, in this case, 10 vectors together. You're adding 10 vectors together. They'd all have to be head to tail. One vector connected to the next vector, connected to the next vector, all head to tail. And then the resultant would be a new vector that goes from the tail of the first vector all the way to the head of the last vector. But ours was just 2. I can type in those magnitudes now, which I believe, actually, I'm not 100% sure I remember those exactly. Give me one more moment. Shoot. Un momento, por favor. No, that's not what I want. Oh, there it is. I didn't have to do that. So it was 30, what was it, 30 and 30 and what? I can't even see now. There it is. No, that's vector C. Shoot, do I not even have it written down? 20 and 25, if I remember correctly. So, all right, let me just give that a try. So I believe, sorry, I still have to go back here and reshare. Window. Almost there. Uh, okay, so I would type in 30. The direction was 45 degrees. And for the other one, I believe it was 5 in magnitude and 20 degrees in direction. And then you'd hit calculate. And then what it's placing down here would be the magnitude of the resultant vector. And in this box would be the direction of the resultant vector. Let's see if we get what we get. Good. So it's what checks out, right? The magnitude we calculated was 53.7 and the direction was 33.65 degrees. 6 in this case, they have a little more precision. So I'm just pointing out there's tools like that. I very well might task the class with performing one vector addition problem at some point in the first few weeks of school. And if you've gone through it, again, you can use some of these vector addition calculators online to verify your results and see if you got it right. All right, I hope that was hopeful. Hopeful. I hope that was helpful. Or I can say that I was hopeful. I am hopeful that that was helpful.